And so this is the next one that's going to be nucleophilic addition. This is actually going to be your elimination reactions right here. You may recognize that naming because we have actually talked about these before. This is just going to be an extension of this, in that these are going to be reagents that are strongly nucleophilic, and so we're going to have results from that. Okay, now this right here is going to be a carbonyl containing functional groups. This one's going to have a leaving group. And so this is carboxylic acids. And you may notice I've mentioned numerous times actually throughout the semester that carboxylic acids have derivatives. They have a whole group that is very similar to them. Okay? And that is where you have a carbonyl, which has that polar pi bond, and then you have a leaving group on that same carbon. And so it gives you this very interesting chemistry where you can do the functions of both of those, right? Okay. You will notice that carboxylic acids are extremely common in something that's important to most of you, and that is biological systems. If anybody looks up here, what do you notice about these compounds? We have esters, we have amides, we have acid anhydrides, we have carboxylic acids. These are all the majority of biological compounds, aren't they? Yeah. We actually have the majority of them listed right here. And so why are these so important in biological systems? Because the reactions we're going to go over now, actually. It's very, very easy to do these sort of leaving group reactions and have these intermediate steps that break up that energy input you need to do, which is very important in biological systems because you can't crank the human body to 200 degrees Celsius, can you? Can't you do 100 degrees Celsius and survive, can you? So, yeah, kind of important. Not as important in organic systems because we can pump that temperature up to 100 degrees Celsius, and we oftentimes do, don't we? But does anybody want to reflux for 3 hours? No. You imagine if biological reactions were like lab reactions? Reflux for 8 hours. Okay. So anyways, these are carboxylic acid derivatives. What you'll notice is they always have two portions to it. They have the polar pi bond right here, and then they always have something that can act as a pretty good leaving group, at least under certain conditions. For example, this right here can act as a pretty good leaving group, especially if you protonate it, right? This right here, again, we can act as a pretty decent leaving group if we protonate it, especially. Again, here's the amides. Again, you can protonate that or add another group to it, and it can be a very good leaving group, right? And then this is actually quite an excellent leaving group because it actually makes carboxylic acid when you leave, right? Can everybody see that? It's actually 2 carboxylic acids or carboxylates that have been joined. And that's your acid halide. This is something with a halogen right here. Chloride's the most common, but bromide and iodide can also be. All right. And so let's talk about some unsuitable leaving groups. What are never good leaving groups? Well, we have ketones, where it's an R group, right? We have a carbon. That's never a good leaving group, is it? No. How about aldehydes? Hydrogen. Hydrogen's never a good leaving group, right? There's nothing we can actually do to make that a good leaving group. Okay? Huh? Yeah, I mean, we could add like a incredibly powerful base, right? But it's likely to strip other hydrogens. Actually, the next hydrogen over here. Yeah. But, yeah, unfortunately. The amines also do not have any good leaving groups. This is just not a good leaving group. The R group, nitriles, don't have any good leaving groups because, again, you have a carbon. Just isn't a good leaving group. And so these are just not qualified for this entire section we're talking about. These carboxylic acid derivatives, because they don't have a good leaving group. By the way, this is a weird terminology that really is kind of infuriating, but organic chemists really love it. And so this normally means if you have something with a bond and it says L, that would be a ligand. They also use this for leaving group, and so you have to take it with context. Okay? In this case, we don't have something that would have a positive charge that would be coordinated to. Okay. And so this would not technically be a ligand. It would be a leaving group in this point. Okay. Unfortunately, organic chemists have a tendency to kind of reuse symbols and just not pay attention to anything else. Okay. People all the time say things like, I like more creative endeavors, so I don't like chemistry. And that, does everybody know that that's total BS, right? Like, chemists have come up with every single shampoo, conditioner, color that you see. Crayola hires chemists. That's how they get their colors. All the paints that you see, all of that stuff, all chemists, right? And so, like Heinz 57, why is it Heinz 57 or 52, whichever one you want to eat? It's the 52nd formulation by a chemist. Yes. So, like, organic chemists, if you're going to talk about the artsy people in any field, the organic chemists, you should be an organic chemist then, are the artsy people in the field. Okay? They are very much about, like, a creative, interesting way to make this thing. And they like to get really elegant, even if it is kind of inefficient. This uses less groups. It's more elegant. What's the yield look like? Well, it only gives me 50% of the yield of the thing that you did 3 steps. But well, okay. They're the very artsy type. Okay, so if you ever wanted to go into a very artistic field, in fact, one where you're basically making like bespoke projects, and you're acting like an artist, but with molecules. There's a whole field of it, which is synthetic chemist, where they make compounds and they make one-offs so they can do anything they want, be super creative with it, and as long as they can get the product, right? So you'll notice that they tend to be kind of weird, that they just like use symbols and don't pay attention to any other field. Damn organic chemists. So this right here is an ester. This is carboxylic acid derivative. If we put this right here with this strong base in methanol, what we're going to see is we'll actually establish an equilibrium where we can exchange these groups right here. Because notice again, this right here is a carbonyl, right? And so that's an electrophile, isn't it? Okay. That right there is a nucleophile, isn't it? Not an incredible one, but it's as good of a nucleophile as this would be. And so what you end up getting here is you get an attack on the carbonyl. And so you attach it just like you would like an SN2 or addition reaction, right? Okay. And then this group right here is a pretty decent leaving group. And so what ends up happening is it then leaves, doesn't it? And you get swaps. This gives you 86% yield impact, which is pretty decent. Anybody have any questions on that one? Makes some sense? Okay, let's look at the mechanism. So again, this is just going to be the same steps that you've been used to by now, hopefully, and have practiced more than you probably wished. But, chemistry, organic chemistry is a chemistry of practice, right? And so you're going to get this nucleophile here attacking the positively charged carbon. The electrons on this double bond are going to go up on the oxide. Anybody ever heard of an oxyanion hole? No? Ooh, those damn biologists. A little disappointed in them. How about you? No? Oh. Okay. If anybody right now is in biochemistry, you need to give Dr. Phillips a hard time. You totally do. Okay? And if you take her class and she does not mention oxyanion hole, you need to give her a hard time. Okay? Tease her low. So what an oxyanion hole is, it's one of the most common, in fact, reactive spots in a enzyme. Okay? It's in fact one of the most common uses for an enzyme. and it stabilizes this species right here as a catalyst. And so this right here is an incredibly important biochemistry reaction, actually, but also very important industrial and organic chemistry reaction. A weird fact about this is we are actually starting to make our own enzymes for specific substrates to do these reactions right here very efficiently. Like bespoke enzymes, not made by organisms. Okay? This is like a huge field of research. And if you wanted to get into big money research in the next like 10 to 20 years, but it's a little bit risky because you actually have to produce. You're not getting paid by somebody to do it. Well, you're getting paid, but not much. Then this would be one of the areas you go. Okay. Anyways, so note right here, we create this tetrahedral intermediate. This is going to be what's referred to as the tetrahedral intermediate. Or the oxyanion intermediate. Okay, sometimes also referred to as the oxyanion tetrahedral intermediate, if somebody wants to get super specific with it. This is going to have two spots that can be good leaving groups. What do you notice about this part of the reaction? It is an equilibrium, right? And so one of these two leaving groups is going to leave. If this one down here leaves, then we go forward in the reaction, and that's the nucleophilic elimination. Okay. By the way, you'll notice this entire thing is an equilibrium reaction. So as you build up concentration here, you'll actually start going backwards as well. Okay. Typically, when you do these reactions, you actually need to go ahead and drive it forward in some way. And so you'd put something that would remove one of these. For example, right here, we have a longer carbon chain here. So if we do something that decreases these alkoxide solubilities, we'll actually remove this, right? Can everybody see that okay? We'll drive that reaction forward, in fact. Okay, so we swapped the group, right? Really, it's just half an addition with an SN2 reaction, isn't it? Or another way of saying that is it is a nucleophilic addition followed by a nucleophilic elimination, right? We just do it all in one go. Or another way of saying that is a nucleophilic addition is an unstable intermediate. Okay, now right here, this is the reaction for this. And so we see that we have fairly low energy reactants here. They're going to go up very, very high and have a very high transition state energy right here, which is that oxyanion intermediate. And that's why in physiological systems, they need a catalyst to do this. They need to break this energy barrier up. Okay. In organic systems, we typically do use some sort of catalyst, but you could drive this forward with just heat. Okay. This is going to give us this high energy tetrahedral intermediate. You'll notice that in this case, this is not resonance stabilized. And so that's a difference from one of the previous reactions we had looked at where that one was resonance stabilized, right? And so this energy barrier was much lower. Okay. Once we're up at the oxyanion intermediate to the tetrahedral intermediate, we're going to have a very small energy barrier going either way. You can go either way. This is a reversible reaction. And you're going to very quickly go to one of these products, and that's the product right here. Now, one of the things I would like to point out here is that these structures here that are the reactant and the product, these are resonance stabilized, right? Because you have these oxygens that can put their electrons into a double bond with this. In this case right here, the tetrahedral intermediate, you have 4 bonds already, right? And so you don't have a double bond to move, do you? It can't do the resonance stabilization. That's one of the things that makes this so high energy is the fact that you lose that resonance stabilization that lowered the energy in the first place. Okay? And whenever you're talking about carboxylic acids, these carboxylic acids across the board all have resonance stabilization. Can you see that? They all have lone pairs next to a double bond, right? So they all have some degree of resonance stabilization that they can do. Okay? In fact, this one has a really interesting resonance stabilization, doesn't it? It can go on both sides. Isn't that kind of cool? By the way, the acetic anhydride you used, that's that. Okay. So let's talk a bit about thermodynamics and reversibility here. These are going to have a similar charge stability because they're both alkoxides, right? So the difference between them is going to be very, very small. Whenever you're looking at this reaction thermodynamically, you're going to have almost no movement because what you make is almost the exact same as what you're actually putting out in the end, right? So your product and reactants, extremely similar, right? Okay. This is a reversible reaction. Now, you will note that we kind of are going back and looking at something that's a little different than a previous reaction where it was irreversible, right? And so base-promoted trans-esterification reactions are reversible. It's not true of all nucleophilic addition-elimination reactions, though. So don't take all addition-elimination reactions, nucleophilic reactions, as being reversible because of this. Okay? This is just an example of one that is actually reversible. And again, this has a lot to do with the fact that these energies here of the reactants and products are almost the same, right? So if you can go forwards in this reaction, you have enough energy in that system to do the forward reaction, you have enough energy to do the reverse reaction as well. Okay? Can everybody say that okay? Rather than look like a cliff, it looks like a normal hill, right? So if you can go one way across it, you can go the other way across it. All right, so let's look at the acyl substitutions. This one is benzyl chloride right here. And here we have a alkoxide again. This one's a lithium one, actually, which is kind of interesting, but not really here or there. It could have been in sodium as well. And so what you'll see here is we do the same sort of reaction on this. We again get 84% yield. And it doesn't ultimately have a huge amount of effect on the reaction. But it is a benzene group right here. And so let's look at some of the thermodynamics of those real quick. Okay, so when we do this reaction here, we have this chloride, it's a good leaving group. We're going to attack that carbonyl again. The electrons are going to go up on the alkoxide. That's going to form this tetrahedral intermediate again. And then the chloride's going to leave. What do you notice about your arrows in this case? Is that equilibrium? No, this is one direction, right? And what's the difference here? Is that a OR? It's not an OR, is it? It's chloride. Chlorides are better leaving groups than alkoxides, aren't they? Yeah. This is more stable than this one. Okay. And so this makes it look more like a cliff, right? Where it's going to be much harder to go backwards than it is to go forwards. Okay. Okay. So again, we have that nucleophilic elimination, we get the chloride, and we get the ester here. Notice it's extremely similar. The only real difference here being that we're now doing this with the chloride being the leaving group. So there's actually no reaction with all combinations of this species right here. This would be an ester trying to react with a chloride. Okay? This would be trying to go the reverse direction with this. And if we think about this right here, right? What we're looking at is which side is more energetically stable, right? Which side is lower energy? And so the side of the reaction is going to be favored if the nucleophile is substantially more stable than your leaving group, right? With a negative charge. And so in this case right here, the alkoxide is a lot less stable than the chloride, right? Everybody's okay with that? Okay. NaCl doesn't react with a lot of stuff, does it? No. Otherwise, using table salt would be a hell of a lot more dangerous than it is, right? Hopefully everybody can see that. Okay. So in these reactions, you may have noticed that we had these different functional groups that were leaving groups in the reactions I showed you before, and in the different carboxylic acid derivatives, right? And so this actually leads to a what's called the stability ladder, okay? As you go along the stability ladder, you actually get less and less stable species, okay? So let's go ahead and look at this. This is the energetically favorable species right here on the bottom. As we go up the ladder, we're getting less and less stable species and more reactive species. Okay? So if we have the option of two different sides of a reactant and product pair, the one on the bottom is the one favored. If that happens to be in reactants, no reaction is going to occur. If that was in products, we'll get that product. Okay? They're pretty easy to predict, actually. So carboxylate anions, they're the most stable. What do you see all over the place in biological systems? All over your life, everywhere. Carboxylates, right? Yeah. All over the place, especially in Tennessee where they put vinegar in everything. Carboxylates. Then the next one up is going to be amides. They're quite stable, but compared to carboxylates, they're less stable. Okay? And so you can react amides to create carboxylates. Notice these right here would actually be your leaving groups. This is why this is so stable. Is if the oxygen with one negative charge leaves, it's going to have an O2 minus. It's incredibly unstable, right? And so driving this reaction for that O minus to leave is going to be extremely high energy, very difficult to do. Okay. This one right here is actually the amide. It would have a negative charge on that nitrogen. This is the ester in carboxylic acid. Notice there's a difference between carboxylic acid and the carboxylate, and that's that we have no charge on the carboxylic acid at that point, right? Okay. And so when that leaves OH minus, that's more stable than O2 minus, right? Okay. And so that's less stable as carboxylic acid than a carboxylate. Ester is this about the same. There's not a lot of difference here. Alkoxides and OH minus are very similar, right? Yeah. Not a huge amount of difference in energy. Notice that acid anhydrides are actually quite a bit more reactive. That's why we used them in quite a few reactions, actually. And that's because when you leave, what do you create? Anybody make aspirin back in the day? Yeah. What did it smell like in that lab? Vinegar. It smelled like vinegar, didn't it? And that's because it creates carboxylate. Yeah. And so your leaving group's actually carboxylate. It's resonance stabilized. It's actually quite stable. So this is an example of a pretty stable leaving group, actually. And then, of course, we have the leaving group chloride. Chloride is a pretty good leaving group, isn't it? And so the acid chlorides are quite reactive. By the way, the acid chlorides are very reactive, especially if they're on something high energy. And they can be a hell of a thing to keep from reacting. Yeah. They have very limited shelf lives. Acid anhydrides also have limited shelf lives. In fact, there's some bottles we have of the acid anhydrides over in the lab in the flammable cabinet that if you open them up, they smell like vinegar. And that's because they've been reacting over the time we've had them, and now there actually is vinegar. We've actually made carboxylate with the moisture in the air. Okay, will this reaction shown here take place? If it will, draw the complete detailed mechanism and predict the major products. Try it out. I'm going to go grab some water while you guys are working on the mechanism. I'll be right back. Okay. All right, folks. Anybody still making good progress on this? Yeah, or two more. So, what do we have here? Yeah, that's the carboxylate, isn't it? Sodium's going to leave. We'll have a negative charge there. And so it's the conjugate base of carboxylic acid. Okay. And then over here we have that chloride, right? The acid chloride. Okay. And so which one's more reactive? Which one's going to be the one that's the better leaving group? Chloride, yeah. And so reaction's going to take place, right? And so you take the negative charge. That's going to be your nucleophile. This is going to be your electrophile. You attack with the nucleophile, attacking the electrophile. That's going to bring this double bond up onto the oxygen. Does everybody understand why this step always happens first?
Because the oxygen is grabbing the electrons from the carbon there, coming more forward.
Yes, but so you have two options, right? You could put the electrons on the chloride so it leaves, which it ultimately does, doesn't it? Or you can move the pair of electrons that are in the double bond up onto the oxygen, which is what actually is happening, isn't it? And so when you have delocalized electrons, because they're not between two atoms, those can always do things first. They're faster, right? And so that's what you're always going to get. You're going to get attack, and then the electrons in the double bond, lone pairs, those sort of things, double bond in this case, are going to move first because they're delocalized. They already are, on their own that they can move quickly. Okay. And that's going to give you your tetrahedral intermediate. That'll be the nucleophilic addition step. And what you're going to see here then is they're going to come back down because this is not the most stable product you could have made here, right? It's the fastest of these things you can make from doing this. It's not the most stable, though. And so they're going to come back down, and that's going to reestablish your double bond. That electron density is then going to push one of these species off. In this case, this chloride here is thermodynamically favorable to leave, right? And so this is going to come off, and that's going to give us the acid anhydride. Anybody have any questions? Did I lose anybody? Okay. Okay. And again, the major product for this is definitely the acid anhydride, right? Because the chloride is much more stable when it's left, when it has left. Okay, so let's talk about some of the reactions with an ester with a hydroxide. This would be your saponification. And let's talk about the reverse of that reaction. Does everybody recognize saponification? Did you guys ever, this is making soap. Okay, this is the reaction. So if you make soap, or if you use soap, this is the reaction used to make soap. Okay. If you ever want to really get a movie with a lot of soap making in it, that its entire theme is soap making, it's Fight Club. Don't actually watch that movie. I think it's making. I mean, it is like everything about it is making soap, but it is not a soap making movie. Do not watch that. I don't like knowing what you're getting into. So this is going to be an irreversible proton transfer here. And that's because we have the alkoxide here that's going to take the proton here. We're going to end up with a resonance stabilized product here, which is your carboxylate. Now note that, again, we have a very large energy difference between our products and reactants. So under these conditions, this is not going to actually be able to go backwards. Okay? Everybody okay with that so far? Okay. Note, why doesn't any further reaction take place? Yeah, so we got a weird thing going on, don't we? Like if we were to look at carboxylic acid versus an ester, carboxylic acid and ester should be about the same, right? So we should be able to get some reaction going here, shouldn't we? If I were to just give you these reactants, you'd probably go, well, that's basically what he showed me right here, isn't it? That's basically this reaction, right? OH and OR, they're on the same level on the ladder, aren't they? See that? I should get that reaction. Okay. Why am I not getting that reaction? Why do I get this reaction instead? Am I actually comparing the carboxylic acid to the OR, to the ester? Are those my actual species that I should be comparing? No. The species I need to compare are the alkoxide here, the ester, right? Versus this one, which is the carboxylate. Because I'm going to make the carboxylate here, aren't I? Okay. And so my leaving group for this, if I was actually to do this reaction, would actually be an O2 minus, not an OR minus. Okay. And so it's very important to remember that acid-base reactions still exist and still are going to happen, and those are likely going to happen first, right? Because protons are much lighter, and so they're going to be the first ones you'll get the reactions for. So notice again, we're not actually looking at an ester versus carboxylic acid, are we? We're again looking at the carboxylate versus an ester. Or another way of saying this, we're looking at this being our reactive species, which is the alcohol, which is not as good of a nucleophile, is it? Okay. And then this right here is going to be, if we have the alkoxide, it's going to try to come in here. But what do you see about this complex right here? It's not positively charged, not neutral. It's negative charge, isn't it? And so when this tries to come in for the attack, it's going to have to attack something that has a negative charge. Okay? And so we're kind of doubly screwed here. This kind of just finishes the entire ability to do this reaction, doesn't it? Okay? And this is why you never see this reaction with carboxylic acid and the alkoxide. You can do the ester and the alkoxide, no problem. You can't do the carboxylic acid with the alkoxide, at least not anything like this. You have to have very different conditions. Okay. Everybody okay with that so far? Okay, fantastic. Okay, so this is going to be the saponification reaction. What we have here is an ester. Typically, this ester, when we're looking at actual saponification reactions people would do to make soap, would be something that would be like cell membranes or fatty acids. Okay, so you'd see this typically done with like glycerol as being the head here. That's the 3 carbons with OH on each of them, and we'd have each of these linked to one of those. Okay, everybody okay with what I'm talking about? Seen in some of your biologies and that sort of thing? Is anybody like, what the hell is he talking about? Okay. Like, I'm talking about biological fatty acids, right? By the way, does this mean that you can do this with fat from a human? You very much can, and the ethics would be an interesting question because there's a lot of fat from humans that from liposuction, right? Ethically, is it more ethical to safely dispose of it and make soap with it, or to keep it as a biohazard?
You make soap with it, you have to make sure people
Yeah,
human soap.
you definitely would. And honestly speaking, the other things that come along with it, I think you're probably right. It probably wouldn't be ethical overall. but yeah. So you can actually make soap out of yourself. Whenever I have people make soap, I always like to joke around that it's the deepest clean you're ever going to get if you put base on you, because it's literally going to eat away at your skin and make soap out of it. So you get nice and deep clean, right? Okay. Okay. And so this could be you right here. By the way, this is actually one of the ways you can get rid of a body. Like the new way of safely and green disposing of bodies is actually this. It's saponification. And so we use KOH in this case. You can use NaOH, doesn't really matter. Oftentimes people use ethanol. They use that to get everything to mix well. It's a part of the solvent, though not usually the only solvent you use here. In this case, it's going to take 60 minutes at 35 degrees Celsius. You don't want too hot of a temperature because the soap will burn. And you get terrible yields if you do very high temperature. You drive off all the water, soap burns, really is a mess. You do need then time. And this is actually where if you guys made soap in lab, you guys' soap always turns out bad because you guys never give it an hour to 5 hours like it needs. Yeah. To complete the reaction, you usually put it in a tote with some plastic lining so you can get it out afterwards, or oil, like spray. And then you leave it for like under the sun for a day or two. So it can do the reaction. Yeah. And do the complete conversion. You usually finish this off with a little bit of HCl with water, or you can actually use, if you're making nice soap for like people to use, you can actually use citrus. So does anybody know what lime zest or orange zest is? Yeah, like very fine shavings of the peel. You can actually put that and mix it in with the soap once you're done. You heat it a little bit to get liquidy, and it'll actually neutralize all the acid and give it a very nice orange scent. By the way, I only know all this crap because I used to work with a couple people that did this as like a side hustle. One of them actually quit their job and started a company. It's like a tens of millions of dollar company. The other one did as a side hustle, but made more doing this than they made at their actual job. Like a 6-figure on this. Yeah, you very much can. And essential oil extractions, which I've taught you how to do now. So. Yeah. See, I'm giving you some business skills. Yeah. So the first reaction in the sequence, that's saponification right here. It literally means soap making. In its Latin, sapo is soap. And this was one of the first cultures that sort of widespread figured this out, particular because they used to like burn the remaining parts of their animals in the fire that makes soda ash and potassium ash or potash. Okay. And those are actually lye, the sodium hydroxide, potassium hydroxide. Yeah. And then the grease would run down into those ashes and create soap. Okay. Not the only culture that ever made it, just the one that has come first. That is most widely spread. So there is a connection, by the way, to decaffeinating coffee in this. And that's the ethyl acetate is actually a common organic solvent right here, used in liquid chromatography. It's also the decaffeinating agent for coffee. And it's because this can actually efficiently extract caffeine from your bean without excessively removing other compounds. And so it affects the taste very little. Also, it's not hexane and it doesn't poison you as much. Okay. Yes, I mean, everything's toxic in the right amounts. Yeah. Did you guys see that the biodegradable plastics might actually be more toxic for you than regular plastics? The starch-based plastics? By a lot? Yeah.
We can't catch a break.
We can't. Like, I kind of have already known this for a while, that the lack of bioavailability for plastics probably means they're one of the least toxic things. The only problem is we use so much of it. Kind of like CO2.
Yeah.
Of the options, CO2 is one of the least toxic things. It's just once you put enough of something out, kind of doesn't matter what it is. Did you guys know there's something called heat waste? Yeah, if you put water back at too high of a temperature, it can actually destroy an ecology. Just literally having a slightly different temperature, like 5 degrees. Yep. It's wild. It's actually quite complex. Oh, yes. Yes. If you did enough, you would actually destroy the ecology. Yeah. The entire ecosystem. Yeah. It's wild. So this right here is pontification, of course. We have the base here attacking the carbonyl. It's going to give us our tetrahedral intermediate, just like we looked at before. This is then going to have the nucleophilic elimination. And so what will end up here is a carboxylic acid at the end of this. Notice that's going to be an irreversible deprotonation that will happen for the next step, which is actually what drives this reaction forward all the way. Is that once you make the carboxylic acid, it can never then go back once you deprotonate it. Okay? And so this last step is actually the one that drives this reaction irreversibly forward. And it will complete, if you put stoichiometric amounts of these things, this will go to completion and consume all of the NaOH. Okay? And you'll end up with neutral compounds. And most of this stuff will actually come off because it's light enough that it evaporates. So you can actually drive this reaction completely forward. If you happen to have glycerol as the thing that's coming off here, that's actually not damaging for your skin. It's quite good for your skin. And so that's not a negative at all. Anyways, it makes your carboxylate group right here. Typically what you do is you can do the acid workup, which is what they're doing here, so they get the carboxylic acid. But that's not normally what you give people as soap. Okay, you don't normally give them the fatty acid, fatty acid. You give them the carboxylate with sodium or potassium. Okay, and that's what soap is. Right? Technically, they're not wrong. This is soap because you can just put it with a base, right, and then you're good to go. But this is not normally what you do to the soap. Okay, normally you have like potassium or sodium. Okay. Anybody know why I didn't say magnesium or iron with it? Anybody know how soap works?
Ions.
Forms micelles. Exactly. So this is the head of the soap right here. So you have a fatty acid tail, and then you have the head. It has a negative charge. And then you'd have something with a positive charge over here. And so you get this ionically charged head that's going to orient out towards water. And what you get are these nonpolar tails end up orienting towards each other. And those are going to create the micelles. If you put it in with grease, these are going to associate with the grease. They're going to bunch up around it and give a polar outside shell for the water to associate with, right? And just like the micelles in your body that transport like food for all you biology people, it's going to lift those and allow those to go other places, i.e. with the water you're washing the grease off. Okay. Okay. Did that make sense to everybody? Okay. What happens if you put iron or magnesium in? What sort of charge does iron have? Yeah, 2 or 3 plus, right? And so instead of getting only 1-to-1 ratio here, right, what we're going to get is the polar heads orienting towards the iron and the nonpolar tails orienting away, right? And then that is no longer soluble in water, is it? Okay. Anybody ever heard of or seen soap scum? No? That's that like white rim that develops on your sinks and bathtubs, especially around drains and stuff. Yeah. You definitely have seen it in the dorms. Because there's no way they're softening the water appropriately. You may mistake it for mold. Sometimes it's a pinkish color, especially if you're using certain soaps.
I mean, like actual black.
Oh. So it's not uncommon for people to mistake soap scum for mold. Because it like ends up all over the bottom of your showers and bathtubs and stuff. And it's like little plaques everywhere. And it can have coloring to it, depending on what soap you use. And so this is soap scum. It's insoluble, so it plates out onto the bottom of your bathtub. It's like a reverse micelle. Okay. Anybody know why you do a cell membrane versus a micelle? So these have single tails, so they can get really close to each other, right? If you have a double tail, they can't get very close to each other. And so you end up with a much broader connection. And they can't actually connect all the way down. And so you end up with a bilayer. So it can be stable. Anyways. Okay. Now we do a little biochemistry and other stuff. Okay. Actually, that was normally handled in the polar, non-polar General Chemistry 1 stuff that you talked about. But sometimes they don't get time. So this is your free energy diagram for saponification. And what we're seeing here is we got the ester. It's then going to react with the OH minus. This is going to give us our tetrahedral intermediate. And again, that's going to be quite high energy. What's then going to happen is you're going to fall apart. That's going to give you your carboxylic acid and the alkoxide. Now notice that has localized charge. It's an intermediate that's going to fall apart really, really quickly, right? That energy barrier for the proton transfer is extremely low, so this can happen extremely fast. Okay? And so what you're going to get then is that irreversible deprotonation. And that's going to keep this from ever being able to go back. Because we're going to extend this back out so it looks like a clip, right? And so again, you get a resonance stabilized carboxylate right here. Very low energy. And then you get the, in this case, alcohol, ethanol. Okay. So this one's going to be some carboxylic acids from amides and the Gabriel synthesis of primary amines. So this is your amide hydrolysis right here. So this one's an amide. See the nitrogen right there off the carbonyl, just like a protein, right? And so we're going to react with KOH. And this is going to give us the carboxylic acid right here. And then your amine right there. Okay. This gives us excellent yield, by the way. This can actually be referred to as an amide hydrolysis because you end up kind of adding water across this thing over the overall reaction. So it's going to be the same sort of reaction as this saponification, right? So we have the amide. We're going to attack it with this negatively charged oxygen right here on that carbonyl. That's going to give you your tetrahedral intermediate, just like before. Notice these are always going to be the same sort of reactions every time. It's extremely repetitive. Okay. Do you guys need me to cover this part anymore? Are you good? Good. Thank you. Anyways, it falls apart. What we're going to get then is the carboxylic acid right here. This reaction's actually unfavorable up to this point right here. This is the point where this reaction would be unfavorable if we were to stop this reaction here. And we would not get much product, if any. Okay. But this carboxylic acid right here is an acid is right next to a pretty good base, isn't it? And negatively charged amine. And so that's going to give you an irreversible proton transfer. And that's going to give you your carboxylate, which is very stable, and your amine right here, which is still a base, by the way. I know it's the conjugate acid of this, but that's actually still base. Okay? So you actually, at this point, have two bases. To finish off this reaction, you use to do an acid workup, but you don't need to. This is actually quite stable as it is. It's not going to go backwards. You would just have basic conditions. Okay? And so you can do an acid workup. That's going to give you this one right here, which will give you the protonated amine and your carboxylic acid. Okay. Anybody have any questions there? Okay. Does everybody know why you use like lemon juice on fish, by the way? It's actually to protonate, to make it acidic, and it's the amine here. So if you give this a charge, that becomes an amide salt, right? Ammonium salt, excuse me. And so once that's a salt, that has a much higher boiling point, much lower vapor pressure, and reduces the fishy smell, which is the amines, right here. So that's actually the same. This acid workup is literally what you would do if you're taking like fish and putting citrus on it. Okay. You can actually do it with any acid. You could do it with vinegar too, which would be this right here. But that sounds kind of gross. All right. This is the energy diagram right here. And what we can see right here is that the amide going to the tetrahedra, very, very high energy intermediate, right? And then once it goes to the carboxylic acid, this combination of species is actually higher energy than this one. And that's because we have a negative charge on a fairly electronegative species right here, right? And we have no resonance structure to help us. And so we don't have quite the resonance structure that to help us. It would have a localized charge on that resonance structure. So this is actually unfavorable up to this point. See that? Thermodynamically, it's unfavorable. It's the next deprotonation step, that proton transfer step, that actually makes this a favorable reaction. Because then you get the carboxylate and you get a more favorable amine, right? A lower energy amine. Okay, does anybody have any questions there? Okay. Note, by the way, that again, if you memorize the ladder here, this is just the ladder, isn't it? Yeah. We've actually just worked the ladder again. So all of these reactions can actually be simplified down to that ladder concept if you want. This is the Gabriel synthesis. And so this is phthalamine amide, excuse me. And that's where you have the oxygen over here, the carbonyl, nitrogen, and on the other side you have another amide. Okay. Okay, and so we're going to put base in with this. This is going to be an alcohol, ethanol. And then the second reaction condition is going to be adding this bromoethane. This is actually going to give us, excuse me, this where we're actually going to react the amine here. So we're actually going to end up attaching this ethane group right here to the amine. Anybody know why that would happen? You don't need me for this reaction mechanism. You guys have seen this like 10, 20 times now. But I have things in a slightly different arrangement than what I usually put them in. What do the first reaction conditions give us? Deprotonation, you got it. Yeah. We have a base. Right here we have something that can lose a proton, right? And so once that nitrogen has a negative charge, what is that going to end up being? It's basic, but it's also a nucleophile, right? Hey, what do we have here? That's an electrophile with a good leaving group, isn't it? Yeah. And so we're just going to attack that, aren't we? In a standard SN2 reaction. Okay. Very good. Okay. And so we can actually then give it basic conditions again in water in this case. The water is important for this next part. And what that will do is this will actually give us the carboxylate and free the amine right here. Okay. And so we get the ethane amine in 57%. We can add any amine we want to this. It can be a whole variety of things, lots of different carbon chains, whatever we want. And we free that, and we get the carboxylates right here. Let's go ahead and look at the mechanism. You guys already got this part, which is, again, the base is going to deprotonate, the proton transfer step. That's going to give us our pretty decent nucleophile. This is going to do the SN2 reaction on the bromo, ethane. And then bromo is going to leave. Now, what we've done is we've actually established a slightly better leaving group here. Okay? And that leaving group is going to be that amine now that we've made. So the next thing we're going to do is we're going to take strong basic conditions, the same sort of conditions we've been doing over and over and over in this chapter, right? You starting to feel a little frustrated with me? Yeah. Okay. It's okay to do this like 10 times. Okay. And so we're going to again do that same sort of attack where we attack the carbonyl again. This is going to give us this leaving group here. And then again, we're going to do it again. And that's going to have the primary amine leave completely. And we'll be left with the carboxylates on both ends. And notice again, that's just same thing over and over. This is actually referred to as acyl substitutions, in case you're curious. And those are the acyl groups. Okay, so let's look at a haloform reaction. All right, so right here we have a methyl ketone. Right there, where it's methyl on one side and ketone. This can actually undergo the acyl substitution when you're treated with Br2. It has to be done in aqueous sodium hydroxide. Then you have to follow it up with an acid workup. One of the products actually is the bromoform. Have you guys ever heard of chloroform? Yeah, very famous in movies and stuff, right? This is just the bromo version. Bromoform. Okay. Iodoform would be that. You get it. Okay. By the way, does anybody know in movies what's chloroform was used for? Yeah. Do you guys know what would actually happen if somebody tried to do that to you?
You'd probably just be like, oh, that smells weird.
Yeah. It would eventually knock you out if they soaked it enough.
They'd have to take away enough oxygen.
Exactly. You'd end up fighting them for about 5 to 10 minutes before you'd actually put them out. So, like, people do that. They actually think, like, it'll work like the movies. They always get caught because their arms are just shredded, right? Because they're sitting there holding the person. They actually usually end up choking them out. And, like, the person fights back and starts shredding up their arms with the nails, right? And so, thank God they usually get caught. And thank goodness that a lot of criminals are pretty stupid. Yeah. The funny part is, for a very short period of time, it was actually used as an anesthetic, but it causes a bunch of other problems. So it hasn't been used in a long time. It's actually quite dangerous to use, and it causes cancer. You can use ether, actually, has no major side effects other than being very difficult to use. It's very difficult to actually measure without very skilled anesthesias. So that's actually comes back every like 5 years, though. Ether does. You know, that's why all those movies have like the burned down hospital as the premise, right? Those are ether rooms that burn the hospitals down. So, all those horror movies. Ether anesthesia. Okay. Okay. So again, you're going to get your whole haloform, and that formula is HCX3. X being a halogen atom. It can be, again, chloro, bromo, whatever. And that's why this is referred to as the haloform reaction, is because you generate a haloform from this reaction. Notice this is one of the ways that you can actually get a methyl converted to a carboxylic acid, right? And so it's kind of an interesting reaction where you can take a ketone with a methyl and you can actually convert it to something that's extremely reactive, and you can do a lot of other reactions with, right? Okay. And so this is the first part of this. It's going to be a repeat alpha halogenation. You're going to do this 3 times. And so what we're going to get is repeated reactions where we halogenate this alpha 3 times. And that's going to be that same pull the H plus off, add a Br to. Pull the H plus off, add a Br to it. Over and over and over. Okay? Eventually, you're going to have 3 bromos on that carbon. This is going to make this a much better leaving group. Okay? And so this is then going to have your normal nucleophilic attack, tetrahedral intermediate, and now you have this much better leaving group right here, okay, which is the halo form. This is then going to be what leaves. That's the nucleophilic elimination again. Note that this is going to be a pretty powerful base. That's actually going to end its own reaction there by doing an irreversible proton transfer, right? And that's what actually wraps this reaction up and drives this forward, is that this is a very good base. It's going to go ahead and take that proton. And once it takes the proton, this then becomes very unreactive in comparison. Also, this is insoluble in water, while this is soluble in water. And so they're going to be in 2 different phases. So you're going to have very little interaction between them. So it's actually, this is an example of what would be considered an elegant reaction, by the way. Very imaginative, elegant, right? Kind of cool. Where it sets itself up to drive itself forward, doesn't it? You gotta love the symmetry there. Okay. Does anybody have any questions? Fantastic. This is actually usually has fairly good vapor pressure, by the way. So you can actually boil these off too, usually. Okay. So why are all 3 halogen atoms actually necessary for this? So you notice we did a methyl here. We didn't do an ethyl, propyl, none of that stuff. So if we only do 2 halogen atoms at that alpha carbon, that leaving group's not going to be stable enough for your acyl substitution. We're not going to actually be able to get attacked by the OH here, where this group leaves. It's only where we have the haloform, we have all 3 halogens on there, that becomes stable enough that we can actually get that leaving. And that's again because remember that each of the halogens is going to pull some of that electron density away from that carbon, right? So it's only when we have all 3 that we can do it. This is actually the negative iodoform test versus a positive iodoform test. So before we had spectroscopy, almost every analytical technique had to be some sort of chemical analytical technique, right? We had to do a reaction that made something visible that we could see, okay? There were some flame tests that could be done, but that's kind of the limits right there. And so this right here is the iodoform test. This right here is the iodoform right there. It is commonly used as a method for testing for methyl ketones through the reaction that we saw up here. So you just do this reaction. You'd use iodine. Anybody know why they'd use iodine instead of like bromine or chlorine? You can get it soluble in water. Yeah. So it actually forms crystals at room temperature. So you can have it in a non-gas state. Which, like, imagine trying to do this test back in an 1800s lab and everything's in a gas state. Imagine doing that in the lab here. Would you want to work with chlorine gas? No? No? Okay. Yeah. And so this was one of the tests you could use. You treat an organic compound with I2 in a basic solution, and it would react. It would form the iodoform right here. And so you'd see these really bright yellow, neon yellow crystals. And you go, methyl ketone. Cool. And then you can do other tests if you're looking for other things. And basically, every reaction would be something you could visibly see the difference between, and would test for that functional group. Okay. Uh-huh. Yeah, sure. Definitely.